Okay, so now we'll begin to talk about two methods for allocating consumption across people in this economy. And there's two classic methods which are tied together. There's an interesting intellectual history about this between planning and competition, competitive equilibrium. And this goes back to this relationship between planning problems and equilibrium problems goes back to even before the 30s, and it's about fundamental things in economics, about the relationship between the intellectual foundations for competition, competitive markets. Why do you think there's a good idea? Adam Smith and in the 18th century and 19th century economies asserted it was a good idea and made lots of arguments, literary, verbal arguments, but they never had a mathematical proof of it. And then on the other side, there were a bunch of people who thought it wasn't a good idea. And there were increasing number of these people in the 19th century. They thought planning was a good idea. Ultimately, some kind of command economy where there weren't markets and prices. So what's the justification for those? So in the 30s, especially at the University of Chicago, someone named Oscar Lange started studying this, and what he found kind of intrigued and surprised a lot of people, and it is that he basically showed that a planning economy could achieve just as good outcomes in terms of efficiency as a competitive equilibrium economy in some ways. And he took that as a victory for planning, whereas the same mathematics could be turned on its head, literally, and be given a case for competition. And these things are going to be tied together repeatedly. We'll come back to this. Okay. So our economy, we have a pure exchange economy where we've got individuals owning endowment in each state of the world. We could think of adding it up, and then want to think about allocating it. So first we're going to study a planning economy. And we'll begin this way. And this is a classic way to start it. We're going to have we're going to call it a Pareto problem. We're going to have a planner, an artificial, imaginary planner, a Pareto problem. So here it is. There's going to be a planner who's benevolent, and he or she can issue commands. He just says, "Give me your endowment, and I'm going to give you some consumption." And so here's what the planner has a welfare function, which I'm writing down now, and it's this, where the lambda i's are non-negative numbers. They're non-negative, and they're Pareto weights. We call them Pareto weights. It's how much the planner loves you relative to other people. So you want a high Pareto weight. That's it. So what the planner wants to do is allocate resources to maximize. So it wants to maximize this by choosing consumption plans for I equals 1 through I. So it's a very large dimensional problem. It wants to maximize this subject to, well, feasibility, a large number of constraints. So remember what feasibility was. We had this CIT of ST, add those up, and that has to be less than adding up everybody's exogenous endowment. And this has to be, how many constraints are there? There's one for every T, and there's one for all ST at that T. So it's a huge number of constraints. So it wants to maximize this subject to this huge number of constraints. So let's solve this problem using a classic Lagrangian method. What we're going to do is we're going to attach a Lagrange multiplier, theta t, st. So there's one multiplier for each t, for each st, and we're going to attach that, one of those to each constraint. It's going to be a non-negative Lagrange multiplier. And then we're going to form this big Lagrangian. So let's just write it out. And it's important to write this out carefully and not sloppily, not skip steps. Because there's famous cases where people skip steps and they made some mistakes. So I'll just write it down. Here's my criterion I'm trying to max. Now I substitute in the utility function, the utility functional for each person. CIT ST, we'll write this down. Pi, now there's my pi t. Notice there's no I, because I erased that. But some famous people put an I back in and studied this problem. We might do that if we have time. So there's no I. And then running out of space plus, now I put my Lagrange multiplier. You could ask yourself, there's never an I. Why isn't there an I on this theta t? Well, there's no I on these constraints. We've summed over I's. So there's a constraint for society, but not for each individual here. That's what quote unquote. Yeah. So I'll put the sum outside. Go slowly. Here's my consumption plan at time t and at node st. So that's my Lagrangian. And now we're going to use the Lagrange multiplier theorem, hoping it holds over these infinite dimensional objects. We're going to maximize this. We want to maximize this over all of these for all t, for all st, for all I. We want to maximize that, and we want to minimize it over the Lagrange multipliers for all t, for all st. That's what our problem is. It's a huge problem. Okay. So the way we're going to proceed is we're going to get first order conditions with respect to everything we want to maximize with respect to. And then we'll make an observation about the thetas. So everything inside is going to be important. This is we're choosing an allocation, and this won't make sense now. This is we're choosing shadow prices, whatever those mean. Lagrange multipliers are related somehow. Lagrange multipliers for planning problems are somehow related to competitive equilibrium prices. That's just a forecast. So let's take the first order conditions, first order necessary condition, with respect to C, T, I, S, T. So if we do that, we get the following. We've set this up, so all we do is we differentiate under the summation sign. We differentiate under the summation sign. So we get beta to the t, u prime, which we know is a positive number, I, CTI, ST, put that in there. And our probability is in there, IT, ST. And that's equal to lambda I. I'm going to write it this way. Inverse. You'll see what I do. I'm violating my rule about skipping one step. Because when we differentiate this, when we differentiate this, here we get a lambda I, beta to the t, u prime, that's what we get. I've taken the lambda I, let me just not write it this way. Lambda I this, that's differentiating with respect to there. And then with respect to Lagrange multiplier, I get a minus, here I get minus theta t, because it's linear in ST. So that's my first order condition. And that holds, how many of those I have? I have these for all I, there's one of these for all I, for all ST, for all T. Huge number of these conditions. State by state, history by history, time by time. Remember, dynamics is a special case of statics. Uncertainty is a special case of certainty. Okay. So now here's, I'm going to use I'm going to take the ratio, call this star. I'm going to take the ratio of star for, and we're going to revisit something for I and 1. For an arbitrary I and 1. And I'll get the following. I'll get UI prime, marginal utility of consumption, divided by U1 prime, CT, one ST, equals lambda 1 over lambda I. So that what that's telling me is, okay, now why did that happen? Why did that happen? Okay, and we can actually start seeing how we could write a different kind of paper. I did not have an I here, and I did not have an I here. So the betas and the probabilities, the discount factors and they're the same, so they divided out. If they were different, I would have also, if beta are different and pi ti's are different, I would have ratios would appear here. Ratios of probability and ratios of discount factors. But I've assumed they're the same, so they drop out. Beautiful. And that's used in huge parts of macro, not all parts of macro. There's a growing literature on heterogeneous beliefs, small but growing literature. And in that case, these ratios do not disappear. There's also there's important papers where different people have different discount factors, betas, and there they don't disappear, but they're disappearing here. So now what I can do is, just a digression, they have disappeared. So this equation implies that we can actually solve for CTI of ST. I'm going to get something important. I'm just going to take the inverse function u prime inverse. That's a function. Under our assumptions about the function, that inverse is well defined and monotonic. And then I get Li inverse L1, that's the ratio of these Pareto weights, U1 prime CT1 of ST. And so why is this of use? This gives me, look at this. This is progress. This gives me everybody's CTI as some kind of a function. The function depends on your utility and my utility, but it's only a function of the first guy's consumption. So everybody's consumption is going to vary somehow smoothly, state by state, history by history, time by time, as a function of this ST. That follows directly from this. So then, now what I can do is I can just substitute this into feasibility. So if I take feasibility where at t st, I will get this equation. It's going to look a little complicated. Ui prime inverse, that's the inverse function, of this big mess. I shouldn't say stuff like that. This quantity. Is equal to, well, this is equal to GDP. That we've defined that, I think above is YT of ST, it's aggregate. So what this tells me is I can solve this equation. This is one equation for each T ST. This is one equation in one variable. And I can solve it for the first guy's consumption. So my strategy is, if I solve it for the first guy's consumption, and then I can plug it back into here. So this pair of equations, I'll call this star and star star. They have sort of a recursive. They have a recursive structure. I'll solve star star for CT1 of ST, and then I'll solve star for everybody else's. This is great. And this is how I solve this planning problem. I haven't shown you how to compute for all I equals 2 through big I. So that's how I solve for the allocation that solves the planning problem. Okay. Now, actually, something remarkable came out of this. So I want you to stare at this. Stare at star star and stare at star. And here's what I'm going to ask you the following question. This is a big theme in big parts of macroeconomics, the theory of income distribution, the big parts of finance. Okay, so here's a question to think of. Does the optimal allocation depend on ST or and then can you does it really depend on something lower dimensional than ST? Two questions. So think about that. And just out of what we've done now, we can get a rather remarkable conclusion. So if we kind of do some back of the envelope work, here's kind of what I'll do. My back of the envelope work. See if I can make myself some space here. Make myself a little scratch pad. That's okay. Here's my scratch pad. If I solve star star, I'm just going to simplify the notation. So star star, that implies that CT1 of ST, that's just some, I'll stare at that function. That's just some function. Some function, F1, might be kind of a complicated some function, but we know, you know what the function is. I'm sorry. Yeah, I'm just gonna just a minute. Yeah, it's just some complicated function, because I have to sum up all of these. I have to sum up all of these. Just a bunch of sum of a bunch of functions, but I can reduce it. I'm going to sum that bunch of functions here. I'm going to reduce it, and I'm going to invert it. So I'm going to call this thing is just a function of yt of st. That's what it amounts to. And then what star is going to do, well, star is just going to say everybody else, I got to do some work to compute what this function is. But once I know the CT1 function, I can just plug it in to star and I can get some little FI function. And what you'll notice is, okay, that's what I claim. Now, I make lots of mistakes, so maybe I make a mistake here. But if I make this, if I say this, look what this says. This says my consumption, the consumption of each person at time t, and history t depends. It depends on this aggregate. It only depends on the aggregate. Of course, I have my own little function. what the planner gives me varies across people, but this function does not vary across time. So that means, in this world of, just to be modern, because you hear this all the time, machine learning and data compression and data reduction, YT of ST is all the planner needs to know to award CT ST I equals 1 through N, through I. Just needs to need to know. So notice the following. If YT some history is equal to YT some other history, it just turns out, in these histories, one is I went here, 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 and I got here, I don't know, and here, 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 but I got here. But if it just turns out that the GDP is the same, if the GNP is the same, then, so what this says is if two histories imply same aggregate endowment, then CTI ST is equal to CTI for those histories. That's a little proposition that we have. So it depends, the allocation depends only on the aggregate endowment at ST. Okay. Okay, that's one remark. And then here's another remark. Just pointing out the obvious. The Pareto weights, lambda 1 through lambda I, they're all positive, are fixed over time in this problem. Why? Well, we assumed it. We assumed it. Okay, it's going to turn out that later, in some other models, there is a sense in which some versions, I'm going to be very careful here, versions of Pareto weights change over time and histories. We're not going to have time to talk about that in this semester, I don't think, but just something to be aware of. Okay, so we have now solved the planning problem. We're all done with the planning problem. And we learned something. Okay, so now we're going to talk about competitive equilibrium. We want to talk about what a competitive equilibrium is. And talk about characterizing it. Okay, so we're going to do this Arrow-Debreu style. And what I mean by that is we're going to talk about markets. We're going to talk about markets and prices and commodities. Because remember the Arrow-Hicks idea that time and chance, models with time and chance, are just special cases of models without them, because we're just going to relabel things. So we have to figure out is, when do markets meet? Okay, so Arrow and Debreu, they're going to give a stark answer to that. They meet once and only once at time 0. They never meet again. Think about that. Markets meet once. Okay. And what's traded? What's traded is CT. I'm going to put a claims to consumption at date T and history ST. That's what's traded. So those are the quantities that are traded. Next thing that's going to enter your mind is what are prices? And we're going to call the prices QT0 of ST. And let me tell you what that means. That means that's the price at time 0. Well, that's the only time the price is relevant, because that's the only time it's traded, for a claim to 1 unit of consumption at time T and history ST. Okay. So at this point, I'm gonna take a 1-minute detour and tell you something that Robert Lucas said that was it's a good thing to remember. What he talked about, made an analogy between Tolstoy's novel Anna Karenina, which begins with the lines that all happy families are alike, but all unhappy families are unhappy in different ways. And what Lucas said was all Arrow-Debreu models are alike. What he meant was, what he was referring to was they have a common mathematical structure. And one element of that common mathematical structure is they have each agent in the model has one and only one budget constraint. Why? Well, markets meet only once at time 0. So all complete markets models have this feature. Okay, so let's write down person I's budget constraint. Okay, here's the way this is going to go. And we're going to just, what does he or she buy? Well, buys a bunch of stuff all at once. Buys, I'm just going to, the left-hand side of this budget console is going to be price times quantity added up when integrated. And the right-hand side is going to be price times quantity added up. Okay, so that's my price. I'm person I. What do I buy? That is what I've just written down is summed over time, summed over all histories, summed over all the things that I bought, price times quantity. I buy all those commodities at those prices, and I am a price taker. And that's what I buy. What do I sell? Well, I sell what I have. What do I have? I have price times, what do I have? I have my endowment. That's all I have. I can't work. I can't do anything to alter it. That's my price times my quantity. And QT0ST, I face that as a take as given. I am a price taker. I do not affect that. Okay, so now the question is, where are the I's? Okay, so I'm going to ask you a question. Where are the I's? Okay, this is something that even, okay, people that go to very good schools make mistakes in this. Where are the I's? That's my first question. In the budget constraint. And where are the probabilities? Because after all, there's uncertainty here. The states might or might not happen. They're governed by probabilities. Where are they in the budget constraint? Okay, so there's two questions. So where are the I's? Well, let's just do a search. They're not here. There's no I here. Why is that? Everybody's trading at the same price. Everybody's a price taker and they face the same price. There's no I here. There's an I here because that's you, your person I. There's no I here and there's an I there. So there's an I in your consumption plan and there's an I on your endowment profile. That's what identifies you. You face the same prices. Okay, where are the probabilities? So let's just go look for them. They're not that sum. They're not there. They're not. That's a price. That's a quantity. They're not on the left-hand side, and they're not on the right-hand. They're not on the right-hand side. So where are the prices? Nowhere. Nowhere. Prices are not in the budget constraint. Let's ask another question. Where are the discount factors? Or if in the more general, And the answer is nowhere. Where are the utility functions? They're nowhere. Okay? So this is really important to remember. So now I'm going to say this. Okay, so what's going to be we can state what the consumer problem is. In a competitive equilibrium. I'm recycling notation. I can, I'll put a dagger here. That's my budget constraint. Competitive equilibrium, the consumer's problem is to maximize over a consumption plan. I'm going to use very concise notation, U of CI subject to dagger. Taking, what does he or she have to take as given? The QTs and the endowment process as given. That's the consumer's problem in a competitive equilibrium. So let's briefly just get first order conditions for the problem. What we're going to do is let's formulate the problem as a Lagrangian. This is going to be key. We're going to discover something interesting. Let's write this out. L twiddle, we want to maximize over T, maximize over ST, beta to the T, UI of CT, I, ST. There's my probabilities. I didn't put any I's on them because of what we've discussed earlier. And now I'm going to put one and only one Lagrange multiplier, and we're going to call it mu sub I. That's my Lagrange multiplier. That's my Lagrange multiplier on my budget constraint, which is T, ST, QT, 0, ST. And I could save myself some space. I could write, that's my endowment. Oops, that's my endowment. And that's my consumption. So the key thing is I have one budget constraint and I have one multiplier, one Lagrange multiplier. On the budget, on my budget constraint. That's it. So why don't, I'm going to stop here. Why don't you get the first order necessary conditions and stare at them. Then do the following. Take the ratio of the first order necessary condition with respect to C, T, S, T, I for I and 1 for person. I'll call this for J. For J equals I, the ith person, and J equals 1. Take the ratio and stare. And now this is more, this isn't rigorous, and stare. Do they remind you of anything you have seen in the past week? I think that's a fun place to stop. Because in posing it this way, you're actually following in the footsteps of some giants, like people in the University of Chicago in the 1930s, some of whom who really loved competitive equilibria and thought it was great, but couldn't quite prove why it was great. And some other people who were socialists, they liked command economies, benevolent command economies, and they thought that was great, but they couldn't quite prove it. Because they're academics, they're talking to each other, but maybe they came to this point and they asked this question: does this remind you of anything you've seen in the past week? Thank you.